Hello student, welcome back to our M.Sc first physics semester second course atoms and molecules, and this is our sixth lecture, and in this course we are studying our fourth module, that is a resonance spectroscopy, and this module is for 1 credit. And in that chapter or in that module we have covered about the ESR resonance spectroscopy, and we started the NMR spectroscopy. That is, we have studied the what is actually NMR spectroscopy. After that we have studied the basic principle of NMR spectroscopy and how we get the spectra of the NMR spectroscopy with the help of flipping of the, or there is a shifting, not shifting, but there is a transfer of energy between two levels in a presence of external magnetic field, and all those happens due to the radio frequency electromagnetic radiation. So all those things we have covered in our previous video or previous lecture. Now in this lecture we have to discuss about the NMR instrumentation. So NMR instrumentation consists of a NMR spectrometer. Like a ESR spectrometer, there is a NMR spectrometer. It has a different parts. So in this video we have to study it. So we have already seen that the basis of NMR experiment is to induce a transition between two consecutive energy levels that results when a nucleus is placed in a magnetic field. Now we have already discussed about the basic principle of the NMR spectroscopy. In NMR spectroscopy, we place a sample in an external strong magnetic field, and due to that there is a transition between two consecutive energy levels or two adjacent energy levels in the presence of radio frequency electromagnetic radiation. So this is the basic principle of the NMR spectroscopy, and due to that we get the resonance at a particular frequency or at a particular magnetic field. So this is the resonance condition in a NMR. One can observe the spectrums experimentally either by varying the external magnetic field, keeping the frequency fixed, or by varying the frequency, keeping the magnetic field fixed. One can change the magnetic field and we can put the frequency constant, or we can do it in a vice versa. That means if we vary the frequency, then we have to keep the magnetic field constant, but the first approach is often preferred since it is difficult to vary the frequency at a very high level of stability, that is 1 of in 10 to the power 7 or better. That means the first approach, that means we vary the external magnetic field and keeping the frequency fixed. So this approach is preferred in generally, because if we vary the frequency and keep magnetic field constant, then it is difficult. That is the second way is most of the time which is difficult to vary the frequency at a very high level of stability. That means if we vary the frequency towards the increasing order, then there is a disturbance in the stability of that frequency, 1 in a 10 to the power 7 or better. So the second way is not preferable, but the first way is most of the time is used. That is we vary the external magnetic field keeping the frequency fixed. So this is in a NMR spectrometer. This principle is also used, or this method is also used. Now what is the construction of the NMR spectrometer? It has different parts. Like this instrument consists of different parts. They are discussed below. First is the sample holder, second one is the magnetic coils, third one is the permanent magnet, and fourth one is the sweep generator. Like as fifth one is the radio frequency, that is a RF transmitter. Sixth one is the RF oscillator. Seventh one is the RF receiver, and last one is, that is eighth one is the readout system or display system. So all those are the different parts of the NMR spectrometer. So we will discuss one by one. So first one is the sample holder. It is a glass tube which is 8.5 centimeter long and 0.3 centimeter in a diameter. That means sample holder is made up of from the glass, and actually it is a glass tube and which has a diameter nearly about 0.3 centimeter and long, that is a length is about 8.5 centimeter, and the sample holder is the glass tube in which we place the sample in a presence of external magnetic field, and this field is applied by the electromagnets, that is a permanent magnet. So this is the sample holder, and which is a very important part of the NMR NMR spectrometer. Now the second one is the magnetic coils. Magnetic coil generates magnetic field whenever current flows through it. We know that the property of the magnetic coils, when we pass the current through that magnetic coils, then there is a generation of the magnetic field. So here also the same function of the magnetic coil. So we pass the current through these magnetic coils and we get the magnetic field, and this magnetic field we can vary with the help of varying the current. Now third one is the permanent magnet. It helps in providing a homogeneous, powerful, stable magnetic field at a 60 to 100 megahertz frequency. That means permanent magnet, which is a electromagnet actually, and which provide powerful, stable magnetic field at the frequency range, that is a 60 to 100 megahertz range, and this range falls into the nearly the radio wave frequency radiations. Fourth part one is the sweep generator. A sweep generator which supplies a variable current to the secondary magnet, then the total applied magnetic field can be varied over a small range. That means if we change the small range, then there is a large variation in the magnetic field with the help of sweep generator. Actually sweep generator supplies a variable current to the secondary magnet so that there is a generation of the magnetic field when there is a flow of current. So this is the function of the sweep generator. Now next, in short, it modifies the strength of magnetic field which is already applied. That means the magnetic field which already applied with the help of coils, but the sweep generator modify that magnetic field, that is a modify the strength of the magnetic field. So this is the function of the sweep generator. Now the fifth part is the radio frequency, that is in short we call it as a RF transmitter. It produces a powerful but short pulse of radio waves. We know that the NMR spectroscopy totally falls in the radio wave frequency region, and in the NMR spectrometer the radio wave frequency transmitter is very important part again, and it produces a short pulse of a radio waves so that the photon of these radio waves gets absorbed when this photon have energy is equal to the energy difference between the two adjacent level, and there is a resonance condition takes place. Now this next part is the sixth one, that is a RF oscillator, that means radio frequency oscillator. A RF oscillator connected to a coil called the transmitter coil transmit the energy to the sample. As mentioned, the axis of the coil has to be perpendicular to the magnetic field. That means RF oscillator is just connected to the coils, that means these coils. Here in the diagram these are the sweep coils, and this sweep generator is connected to this coil, and again radio frequency transmitter, that means this radio frequency transmitter is also connected to those coils. So this is the actual arrangement connected to the coil called the transmitter coil. Therefore they are called as a transmitter coil and transmit the energy to the sample. So the function of the RF oscillator is connected to the coil, and that transform the energy or that transmit the energy to the sample. As mentioned, the axis of coil has to be perpendicular to the magnetic field. In our previous lecture we already mentioned that the axis of this coil is perpendicular to the magnetic field. Then and then we get the resonance condition. Now the seventh one part of the NMR instrument is the RF receiver, that is a radio frequency receiver. A RF receiver connected to a coil called the receiver coil encircles the sample its axis has to be perpendicular to the both magnetic field and the axis of the transmitter coil. Let me see, RF receiver just again connected to the coil, and it therefore called it as a receiver coil, and it encircle the sample. That means totally cover the sample is covered by the RF receiver, so that the its axis has to be perpendicular to the both means to the magnetic field as well as the axis of the transmitter coil. That means the both of them, the RF receiver is perpendicular, or the axis of the RF receiver is perpendicular to both of them. So this is the RF receiver. The transmitter and receiver coils and the sample holder are constructed into a single unit called probe. That means all those three, that is a transmitter coils, receiver coils and the sample holder, these all are three components which are constructed in a single unit, and though this unit is known as the probe, that is a NMR probe, often the necessary small magnetic sweep field is obtained by the use of sweep coils built into the NMR probe. That means there is a necessary small magnetic sweep field is obtained with the help of this unit, and that is a by use of sweep coils built into the NMR probe. Now the next part is the 8th one, that is a readout system, that is a display system on which we observe the spectra or NMR spectra. A readout system consisting of a RF amplifier, recorder. It records the NMR signals which are received by the RF detector. It means recorder and other accessories to increase the sensitivity, resolution and accuracy. That means the readout system consists of different parts again, that is a RF amplifier, radio frequency amplifier, recorder, and the function of the recorder, that is it records the NMR signals which are received by the RF detector. There is a RF detector, and RF detector detect this signal, and this signal again given to the recorder, and recorder records that signal, and we get the actual spectra of the sample and other accessories to increase the sensitivity, resolution and accuracy. That means some other components are also used, or accessories is also used to increase the sensitivity, resolution and accuracy, so that we get the proper spectra, and from that we can study the chemical as well as the physical property of that sample. A schematic representation of these components are shown in the figure. That means all those components are built in a particular manner. So this is the schematic of the NMR spectrometer. So here is there are two coils, that is a sweep coils, and these two coils is connected to the sweep generator. Here is a sweep generator, and in between these there is again these two spinning sample tube. Here is the spinning sample tube, and this is connected to the radio frequency transmitter, so that it transmit the energy to the sample, and then again next process will takes place. And this is the sample holder arrangement in which we can place the sample. Again here is the magnet, that is a N pole, and here is the S pole. This is the electromagnet. This provide the magnetic field to the sample, and which is a strong, powerful, uniform magnetic field. So this is the magnet pole, and this is again magnet pole, that is N pole and S pole. Here is a radio frequency transmitter. Radio frequency transmitter transmit the signal to the coil, and this again given to the this sample. Again there is a radio frequency receiver and amplifier. Here is a radio frequency receiver and amplifier. When the sample goes through this all those things, then there is again we get the NMR signal, and this NMR signal is given to the radio frequency receiver, and again there is a processing, and after that there is a control and console and recorder. Then this signal is given to this system, and again we get the proper spectra of particular sample. So here is the display system, all those display system on which we can observe the spectra. So this is the block diagram of NMR spectrometer. So here are the important parts are the sweep coils, RF frequency transmitter, RF frequency receiver, RF amplifier, and again display or readout system, magnet, that is these two permanent magnet. Then after that this is a sweep generator, this is the sweep generator, and this is the sample holder. So this all are the different parts of the NMR spectrometer, or this is the construction of the NMR spectrometer. Now actually how it works. So working, place the sample in a magnetic field. So here is the sample holder tube, and place the sample which we have to investigate in the sample tube, and all those happens in presence of this external magnetic field. So place the sample in a magnetic field. This is the first step. Now the next is the excite the nuclei sample into the nuclear magnetic resonance with the help of radio waves to produce the NMR signals. Now for the production of the NMR spectrum or NMR spectra, we have to produce the NMR signal first. Then we can observe the NMR spectra. First we have to excite the nuclei of the sample. That means if we place the sample in a presence of external field, we know that then there is a alignment of the nuclei, or the alignment of the magnetic moment of the nuclei in a particular direction, that is along the direction of field or opposite to the direction of field, depending on the direction of the field. So excite the nuclear sample into the nuclear magnetic resonance. So due to this we have the two possibility, that is the magnetic spin quantum number which is a plus half or minus half. So there is a two possibility, and we get the corresponding two energy for that quantum number. So first one is for the plus half and second one is the for the minus half. So we get the two energy states, and there is a resonance between these two energy states. That means there is a energy transfer between these two energy states, that is the nuclei excite from lower energy level to upper energy level, so that when this happen, when the nuclei or the nuclear spin which is present at the ground level, which absorb the photon of radio frequency radiation, and then it will get excite, and after some time it will de-excite, and due to de-excitation again there is emission of photon which have energy equal to the incident photon. So all those happen in presence of external magnetic field, and this all those things happens at a particular condition, and this is known as the resonance condition. And when this happen, then we will get the NMR signals. So in this way we get the NMR signals. These NMR signals are detected with the sensitive radio wave receivers. Here in a diagram there are the radio frequency receivers, and all those things happens here, and after that these signals are detected by the radio frequency receiver, and it amplify with the help of RF amplifier, and again given to the recorder. That means recorder record that signal, and we get the particular spectra. The resonance frequency of an atom in a molecule is changed by the intramolecular magnetic field surrounding it. That means the resonance frequency of atom in a molecule, we know that atom consists of nuclei and electrons, but molecule first consists of atom. So the resonance frequency of atom in a molecule is changed by intramolecular magnetic field. So there is a intramolecular magnetic field. So the radio frequency is changed due to that intramolecular magnetic field. This gives details of molecules, individual functional groups, and its electronic structure. So due to that magnetic field we get the functional group of that particular molecule, or details of the functional group of that particular molecule, and also gives the information about its electronic structure. So in this way we can study the physical and chemical property of that particular sample or molecule. Nuclear magnetic resonance spectroscopy is a conclusive method of identifying monomolecular organic compounds. It means with the help of this NMR spectroscopy we can identify the monomolecular organic compounds. It is generally also used in chemistry, so to detect or to study about the organic compounds. This method provides details of reaction state, structure, chemical environment and dynamic of a molecules. That means if we consider a particular chemical compound and which we have to investigate, then this method or this spectroscopy provide us the details of reaction state and structure of that particular sample or molecule, also give the information about the chemical environment and dynamics of the molecule. So actually these all are the applications of the NMR spectroscopy. Now this is the NMR spectra. This NMR spectra is a intensity versus magnetic field, or we can plot it also with the frequency, where delta is the chemical shift. In NMR spectra, chemical shift is very important, because if we consider the ESR spectroscopy, in ESR spectroscopy we get the splitting due to hyperfine structure of the electron energy levels, but here we get the chemical shift. That means there is a shifting in a resonance frequency from the particular range. So here is a chemical shift in a particular molecule or sample, and due to that at particular position we get the absorption. So this is the absorption, and this absorption is due to de-shielded nuclei and this due to the shielded nucleus. And this is the TMS, the spectra of TMS, where TMS is the standard sample which is used in the NMR spectroscopy. The long form of the TMS is the tetramethylsilane. So this is the standard sample which is used in NMR spectroscopy and which has a chemical shift which is equal to 0. So this is the graph of intensity versus magnetic field. Here is the down field and here is the up field. So the NMR spectrum is a plot of intensity of NMR signal versus magnetic field or frequency in a reference to the TMS, that is a tetramethylsilane. So this spectra is with respect to this standard sample. So here we get these two peaks. This is the NMR spectra. Now what is the de-shielded nuclei and shielded nuclei? So the shielding of protons. Protons means it also one of the nuclei element or nuclei content. So higher electron density around a nucleus shields the nucleus from the external magnetic field, and the signals are of field in the NMR spectrum. That means due to shielding of protons, that means shielding of protons means higher electron density around the nucleus. We know that in atom at the center there is a nucleus, and nucleus consists of proton and neutron, and around the nucleus there is a electron. That means the electron revolve in a particular orbits around the nucleus, but when the electron density is higher around the nucleus, that means the electrons are in a maximum number around the nucleus, they shields the nucleus from the external magnetic field. That means they protect or they shield, act like a shield. The electrons, all those electrons acts like a shield to the nucleus from the external magnetic field. That means they can provide protection from the external magnetic field to the nucleus, and the signals are of field in the NMR spectrometer. That means if we consider NMR spectrometers, due to this shielding effect we get the off field signals, or signals are of field in the NMR spectrum. So for the shielding of the proton we get here this peak, and de-shielding here we get this peak. So these are two different things. Now what is the de-shielding of the protons? Lower electron density around the nucleus de-shields the nucleus from the external magnetic field, and the signals are downfield in the NMR spectrum. That means if we consider the low density of the electron around the nucleus, that means the number of electrons around the nucleus is less, then they de-shields the nucleus from the external magnetic field. That means if we place atom in external magnetic field, and if there are less number of electrons around the nucleus, then these electrons de-shields the nucleus from the external magnetic field, and due to that the signals are downfield in the NMR spectrum, and due to this de-shielding the signals are downfield in the NMR spectrometer. So here is the upfield in the NMR spectrometer. That means here for higher field we get the peak for the shielded nuclei, and here for downfield we get this peak for deshielded nuclei. So here is the electron density is the higher around the nucleus, and here is the electron density is lower as compared to this. So here we get the downfield spectrum or downfield in the NMR spectrum. So due to this property, here we get the peak at the downfield for the deshielded nuclei, and here we get the peak for the upfield for the shielded nuclei, and this is all due to the electron density around the nucleus. So this is the NMR spectra. Now up to this we have covered the basic principle of the NMR spectroscopy, working of the NMR spectroscopy, then how we get the spectra from the NMR spectrometer. All those things we have studied. That means we have studied the different parts of the NMR spectra and how it works and how we get the NMR spectra. But in NMR spectra, the chemical shift is a very important parameter. But what is the chemical shift and how this affect to the NMR spectra, and how we get the NMR spectrum or the peaks in the NMR spectrum? All those things we will discuss in our upcoming videos or in our next video. So in upcoming video we will continue with the chemical shift.